Section 4.4 deals with acid-base reactions. So the first definition is that what we call an Arrhenius acid, which is named after somebody named Arrhenius, is a substance that produces hydrogen ions when dissolved in water. And sometimes we call these protons. So you can see that their generic acid here, HX, dissociates to give us some hydrogen ions. So we have hydrogen ions. And an Arrhenius base is a substance that produces hydroxide ions when dissolved in water. So you can see that our base dissolves to give us hydroxide ions. And an acid-base reaction is also called a neutralization reaction. But I want to talk a little bit more about this H+, okay, this hydrogen ion that we sometimes call a proton. And I want to talk a little bit more about the identity of this very unusual species, because a hydrogen atom is just a proton surrounded by one electron. So H plus is really just a proton, and that's why we call it that sometimes. So with that huge positive charge focused on that little tiny volume, the hydrogen ion attracts the negative pole of a water molecule so strongly that it actually forms a covalent bond to one of them and ends up forming the hydronium ion, and that's what's shown right above this Lewis structure that I'm drawing here. So this is just a space-filling model of the hydronium ion. So we can show this interaction by writing a solvated H plus as the hydronium ion. So it's perfectly acceptable to write the H plus as the hydronium ion. So you should be aware of a hydronium ion. So strong and weak acids. So as far as strong acids go, you need to memorize these 6 acids as the strong acids. So the first 3 are what we call halo acids because the anion comes from a halogen. So we have hydrochloric acid, hydrobromic acid, and hydroiodic acid. You'll notice that hydrofluoric acid is not a strong acid, it is in fact a weak acid. Then the other strong acids that you have to be aware of are nitric acid, sulfuric acid, and perchloric acid. And I can't stress this enough. You have to memorize these for chemistry. The weak acids, there are many, many, many examples out there, but ones you should be familiar with that come up a lot in general chemistry are, of course, hydrofluoric acid, then phosphoric acid, and acetic acid. And acetic acid can be written a couple of different ways. This is called a condensed structure here, a condensed formula. It tries to show you a little bit about the structure of the molecule. This is another way of representing that. Sometimes it's written as CH3CO2. Either way, these are all just different ways of representing acetic acid, which is the main component found in vinegar. Anyhow, as far as bases go, it says here memorize, and it looks like a huge list of bases to memorize, but basically it's the group 1A hydroxides and the group 2A hydroxides. So you should be aware that when you see a group 1A or a group 2A hydroxide, that it's a strong base. There are many, many examples of weak bases, but one you should be familiar with is ammonia. And that one comes up a lot in General Chemistry 1, and it comes up probably even more in General Chemistry 2. So there's no other way that I can really put this except to say you have to memorize the strong and weak acids, or at least the strong acids, and you have to memorize the strong bases. And it's a good idea to have to know that ammonia is a weak base. Anyhow, a little bit more about acids and bases as electrolytes. So electrolytes are just compounds that dissociate to and enable a solution to conduct a current. They conduct electricity by allowing a current to pass through it. So it says here that strong acids and strong bases will dissociate completely. And what's important about this dissociate completely, when we have complete dissociation, the arrow we're going to use for that reaction will be a unidirectional arrow. That means it's completely dissociating or completely going to the products, which are ions that will be found in the aqueous solution. So again, strong acids and strong bases are strong electrolytes because they conduct well in solution. So you can see here, we have some kind of light bulb put in some kind of solution down here, and there must be, either a strong acid or a strong base in there. And the ions enable the current to pass from one electrode to the other, and then it lights up the light bulb like that. If I try the same experiment with a weak acid or a weak base, those dissociate very little, so usually 5% or less. So weak doesn't mean like 50% dissociation. It actually only means, about 5%, so not a lot. Anyhow, And weak acids and weak bases are weak electrolytes because if you try the same experiment that I had on the last slide, they conduct poorly. So you can see the light bulb is dim now, so it doesn't conduct electricity nearly as well when I use a weak acid or a weak base, which again is a weak or are weak electrolytes. So let's take a look at a question here. It's just a good question about interpreting a problem as far as I'm concerned. It says here, how many hydrogen ions or H plus ions are in 25.3 milliliters of 1.4 molar nitric acid? Well, the first thing that I would do here is I would ask myself, what do I know about nitric acid? And if you memorize the list of strong acids, you'll know that nitric acid is a strong acid. That means it's going to undergo complete dissociation. So we don't have to use an equilibrium arrow. It's going to completely dissociate. Let me show you what I mean by that. So if we write down the formula of nitric acid, so it's HNO3 aqueous, what's going to happen in solution is it's going to dissociate completely into the hydrogen ion plus the nitrate anion. So there we go. And again, this is complete 100% dissociation. So how much nitric acid am I starting with? How many moles of nitric acid? Well, I know that I had 25.3, so I have 25.3 mils of a 1.4 molar solution. So the first thing I would do is convert the volume into liters, so I could just divide that by the fact that there's 1,000 milliliters in a liter, so those are going to cancel out, and I'm going to have 0.0253 liters. So if I rewrite that 0.0253 liters, and I know my concentration of nitric acid, which is 1.4 moles of nitric acid in a liter, well, I can look at my balanced equation, and I know that when I have 1 mole of nitric acid, I'm going to get 1 mole of hydrogen ions because it's going to dissociate completely. So I use my balanced equation, and I write for every 1 mole of HNO3, I'm going to have 1 mole of H plus ions. But the question is asking us, how many H plus ions do we get? Well, then we know that in 1 mole of H plus ions, there's going to be Avogadro's number of H plus ions, so I'll put that in here. So it's 10 to the 23 H plus ions. Kind of running out of space here. Anyhow, so if I punch all of that into my calculator, I should only have 2 sig figs because there's only 2 sig figs in my concentration, which is 1.4 moles per liter. So I punch all that in, and I get 2.1 times 10 to the 22nd H plus ions.